Ryong-sun Pu from Advanced Institute of Technology and 성균관대 University. Before my talk, I'd like to express my appreciation to the organizing committee to invite me to talk about one of my research activities. Today's talk is the development of flexible displays. Next, please. Future, this is flexible. Flexible display is expected as a future display. Low cost, large size, roll-over display have many applications as shown in these pictures. Flexible plastic display, rollable electron display, and wearable display, and so on. Next. This picture shows key components of flexible displays. Flexible display is composed of the following three parts: display, driving, and substrate. And for display devices, electrophoretic display, liquid crystalline display, orange LED, and I'd like to explain about quantum dot OLED too. And for the driving devices, polysilicon TFT, amorphous silicon TFT, and organic TFT. And for substrate, conventional glass substrate should be changed to the plastic film to fabricate flexible displays. Next, please. This is electrophoretic displays. In fluid microcapsules, there are positively charged white pigments and negatively charged black pigments. And these microcapsules are sandwiched between two electrodes. And when we apply the electric fields, white and black areas comes out on the surface, depending on the polarities, and generate the image patterns as shown in these pictures. Actually, ebook with this process is now solved by Sony and Philips. And color display using color filter is now under development. Next, please. This picture shows the structure of printable flexible OLED. The organic layers, including the light emitting layers and the charge transport layers, sandwiched between the top electrode and the transparent bottom electrode are shown in these pictures. Next. In order to realize a flexible display, flexible OLED, there are some technical issues to be solved. Printable OLED materials, especially glue materials, is important. And process technology, encapsulation technology, and flexible substrate. Next. For organic LED, there are two types. One is a small molecule OLED, and another one is a polymer OLED. Small molecule OLED was developed by Dr. Tan and Eastman Kodak in 1987. It was fabricated by the vacuum deposition techniques. And the polymer OLED developed by the Richard Friend at Cambridge University in 1990 by coating the polyparaffinium bidene shown in these pictures. Next. Now this is a small molecule OLED. Shown in these pictures, there are many layers on the substrate, anode, and the hole injection layer, hole transport layer, emitting layer, and the electron transport layer, and cathode. There are the 4 layers are required. However, Small molecule can make a multi-layer structure by vacuum diffusion techniques. Then whole transport layer and electron transport layer can be used to get a good charge balance in emitting layers. However, polymer is not easy to make a multi-layer by the solution process due to co-mixing problem. Then whole transport and electron transport moieties should be incorporated in polymer chain to get a good charge balance. Next. So this is a polymer LED between two electrodes, anode and cathode. The P dot, it's a whole injection layers and emitting layers. Principally the two layers. It's much simpler than the small molecule OLED. Therefore, light emitting polymers in emitting layers should have functions of not only emitting but also the transport for electron and the holes together with charge balance. Next. So this is the concept of molecule design for light emitting polymers. In one polymer chain, electron transport, hole transport, and emitting moieties are principally incorporated. And in many cases, electron transport and hole transport moieties have a function of emitting. And the electrons are formed in transport moieties by recombining electrons and holes and transferred to emitting moiety for light emission. Next. This picture shows the light emitting polymer for pentafluoride, polyfluorine, polyparaphenylene, polyparaphenylene, and recently the phosphorescence polymer is also under development. Among these materials, development of blue light emitting materials is especially important. And for the blue materials, polyfluorine and polyspiral are the most well-known polymers. Next. This picture shows the known blue light emitting polymers, including fluorine and spiral as the basic monomers. And these fluorine and spiral co-polymerize with the whole transport moiety, electron transport moiety, and emitting moieties as shown in these pictures. Next. We have also developed our own fluorine and spiral-based polymers co-polymerized with the whole transport and emitting moieties. And these are yield spectra, and this is the current efficiencies. Shown in these pictures, yield spectra is generated from the fluorine moiety without second monomer. It's a curve of the green curves. And once the second monomer is incorporated, interchain and the intrachain external migration occurs. Then yield spectra shift to the longer wavelengths for the efficiency. Second monomer, there is 10% is incorporated. That's red color curves, and 50% is black color curves. And we achieved 8 candela per amperes efficiencies. Next, please. Next, lifetime. Lifetime behavior of blue yield devices. Aging curve and the voltage shift at constant driving current are shown here. This is the time, this is a log scale, and this is the luminance, this is the voltage. As shown in these pictures, as the luminance decays with time, and the voltage shift in the higher voltage. And this voltage increase can be attributed to the following two reasons. One is the increase of bulk resistance of light-emitting polymers due to the drop of the charge carrier mobilities. In our different experiments, the electron mobility drop is much higher than the whole mobilities drops. And secondly is decrease of charge injection efficiency. Next. Here, decay curves. This green curve is 50% drop, and the red curve is drop to the 0%. That means a completely dead device. And driven and undriven yield spectrum shows totally the same yield spectrum. This is a pure spectrum. Black curve is undriven yield spectrum, and 50% drop is green, and totally dead device is red. And also we can see the no spectral change. Shown in these pictures, completely dead device even, and only 33% appear drop because of that. That means 2/3 of light-emitting polymers is still alive in completely dead device. Next. We did the reverse engineering after driving devices to see what happened inside the films. These pictures is peer images after the washing out of the cathode with hydrochloric acid, and this is and then after washing out emitting rays with chlorobenzene. This rectangular area is a driven picture. That means there is the electrode with a rectangular shape. After washing out the electrode, we observed the pure reduction, the gray areas. And after washing the emitting layers, insoluble layer was remained, which is degraded materials. Then insoluble layers still have the same photoluminescence spectrum, even so. We have measured also the HOMO levels of driven insoluble films by AC2 photoelectron spectrometers. Black dot is undriven, and the red dot is shows driven curves shown in these pictures. HOMO level of the insoluble film was not changed, the same HOMO level. And also the same photoluminescence spectrum after, even after driving, which I have mentioned just before, suggests that the light-emitting polymer is incorporated in the electrochemically formed insoluble insulating materials. Next. Then, from this information, we suppose that the light-emitting polymer in the emitting layer electrochemically degrades to form insoluble insulating materials. It enhances the resistance of emitting layer and prevents the injection of holes in the electrons, so that efficiency and brightness of yield device decreases. Next. This picture shows the lifetime progress of organic LED. Lifetime for TV application is 30,000 hours at display brightness 300 candle. This is a small molecule, and this is a polymer OLED. Shown in these pictures, small molecules almost can apply to TV applications. However, polymer is needed to be developed more for lifetime, especially blue, although it is steadily improved. Next, process technology. Low-cost and large-size process technology should be developed. This picture shows a comparison of the batch process and the continuous process. And in the case of the batch process, silicon semiconductor, SiO2 insulator materials deposited by the vacuum deposition and sputtering techniques on glass substrate. On the other hand, in continuous process, printable semiconductor materials and insulator materials are coated by printing and roll-to-roll process on plastic films, which can be expected to reduce the manufacturing cost very much. This picture shows the printing process technology for the flexible display, contact printing, offset, gravure, screen, inkjet, nozzle, and related processes. Among them, inkjet process and related process are now most intensively developed. Advantages of the inkjet process is a simple process and efficient material availability. However, ink formulation is required and reliability is not yet established. Related process, laser-induced transfer imaging processes, and advantages than the high resolution. Only a few microns patterns can be possible to make. Multi-layer stacking is also possible. It's also the good advantage. As an issue, adhesion to underlayer and uniform roll coating or donor films, it's not so easy because the donor film is so thin. Next is the quantum dot OLED. This picture shows the possible application areas of quantum dot described. As you know, the quantum dot is a nanoparticle of semiconductor. Its photophysical properties quite unique, which is different from the atom and bulk materials. In the application, display areas is light emitting devices, and in energy areas, solar cells, and quantum dot biosensors and quantum dot memories. In order to realize these applications, there are some technical issues. Quantum dot should be monodisperse colloidal in terms of the size, shape, and internal structures. To solve this technical issue, surface chemistry is key, very important. To fabricate the quantum dot, there are generally two ways: molecular beam epitaxy and ultra-high vacuum. This technique is well known in organic semiconductor device areas. In this case, a very expensive instrument required. The second is a wet process. To fabricate a flexible display, we choose this wet process. As shown in this picture, in the round bottom flask, cadmium compound and alphatic acid mixed in the solvent and react with the sulfur and the selenium precursors to form cadmium selenide sulfide of the quantum dot. And the core part is cadmium selenide and shell part is cadmium sulfide in this case. As shown in this picture, quantum dot shows a very sharp, strong, and symmetric PL spectrum. And quantum dot can tune the color by controlling the size, shape, and the composition of the quantum dot. And also the efficiency of the PL's photoluminescence of the conductor is very high. Then conductor covers a broader area than the CRT color reproductions. Then, so the conductor can realize a true color display as it is a high color purity. This is the energy diagram of conductor OLED. Between ITU and cathode, whole transport layer, whole electron transport layer, whole broker layer, and the emitting layer of conductor sandwiched between two electrodes. And conductor is used as a light emitting material. And in order to improve the recombination in conductor, these other layers are introduced. Here it is important to make a uniform single monolayer of conductor to enhance the efficiency. Because conductor is a good light emitting materials, but it is not good transporting materials. For conductor to employ the OLED device, we evaluate the EL spectra, efficiency, brightness, and current density for the RGB conductor OLED. As shown in these pictures, EL efficiency for RGB become very high. Red color is a 4.4 candela per ampere. Green color is a 2.3 candela ampere. But among them is blue is really outstanding. We could achieve 1 candela per ampere. It was used to be the 0.01 candela per ampere. This value is practically useful. The practical devices. But still, we have several important issues, particularly for the lifetimes. Next, please. And also, we could fabricate the micropatterns of the conductor films, as shown in these pictures, with this photographic processes. Next. Next is organic TFTs. Advantages of the organic TFT is a low-cost film formation by printing the low-flow process and thermal evaporation. Even the thermal evaporation at low temperature, less than 150 centigrades. Then plastic film can be used. Each large area coating and new application is also possible. However, there are some issues. Rather poor performance compared to the silicon transistor, and reliability is not yet proven. This table shows the organic semiconductors. Pentasene, organothiophene, lubrin, and so on and so on. In this table, the lubrin shows the highest mobility, but it is a single crystal. At this moment, with the film, pentasene shows the highest mobilities. This table shows the requirement of the TFTs for displays. In case of the ebook, high performance TFT is not required compared to LCD and organic LED. For ebook, 0.01 in mobilities and 10 to 4th on-off ratios are acceptable. However, organic LED requires higher mobility and larger on-off ratios. This is the structure of TFTs. Source, drain, gate. And on the gate insulator and semiconductor layers are formed. There are three key issues for pentasyn TFTs. Pentasyn deposition, control molecular arrangement, and microcrystal structures. It is important. Metal semiconductor contact control the current injection, and gate dielectrics is a substrate for the pentasyn deposition, and control interface properties between semiconductor shows a high performance for TFTs. Pentasyn is a conjugated molecule with a linear shape as shown in these pictures. Then pentasyn tend to form a well-ordered structures and easy to form a two-dimensional film by simple thermal evaporations as shown in these pictures. This is a pentasyn crystal domains as shown in these pictures. This microcrystalline is formed by accumulating the two-dimensional films vertically. Then high carrier mobility can be expected. Next. This is a pentasyn growth behavior. These pictures taken 0.51, 2, and 15 minutes after nucleation. As shown in these pictures, each grain is getting larger as the deposition continues. And once each grains contact each other, each large grains getting larger by consuming the small grains, and end up with around 2 micron size. And thus the two-dimensional nucleation growth behavior is observed, and it explains high mobility of pentasyn fields. And this XLD shows clear peaks, which also suggests that thin film phase is dominant. This picture shows the grain size is closely related with the mobilities. This is the number of grains per square meter, microns. This is the mobilities. Shown in these pictures, a larger grain shows higher mobilities. Another important materials for organic TFT is gate dielectric materials. Required properties for gate dielectrics is good for pentasyn growth to get a high mobility, and should have a low leakage current for the high on-off ratios, good chemical resistance, spinel metal, and high case. This table shows the performance of gate dielectrics by several research organizations. Penn State University in 2001 reports the mobility is around 1. It's actually a very good mobility. It is almost the same level as more silicon by using the octadecil trichlorosilane treated SiO2. And in 2 years later, 3M reports mobility 5 by using the polyalpha methyl covered aluminum oxide. It is wonderful results. We also developed our own side gate insulator materials. Side 1 is a derivatives of polyvinyl phenols, and side 2 is new hybrid materials, including the transition metals. Shown in this table, side 2 shows a good performance for TFT. Then we could achieve the mobility 7, and on-off ratio is 10:6. This picture shows the performance of side gate insulator after chemical and thermal treatment for photolithographic process. It is very important to fabricate the panel. This is the process flow. In this flow, there are several various kinds of the chemical and thermal treatments. And generally, these chemical and thermal treatments causes performance drop, seriously causes. This is a gate voltage and this is a drain current. This is before treatment, radicals, and blood cavities is after treatment. It was quite lucky. Our side gate insulator doesn't seriously degrade with this treatment. And then we fabricate the 15 inches LCD panel with this pentasyn TFT with Samsung Electronics companies. This is the largest size and the highest resolutions. And this is a pentasyn TFT. Thank you very much.